Hello everyone, I'm ShiyiWang. For this Machine Learning Module 1 assignment, I've chosen the abalone age prediction problem using the UCI abalone dataset. I will follow the notebook structure to discuss four core aspects: data processing, model selection, bias variance trade-off, and validation methods, presenting actual results from my implementation. So before we run the codes, we need to know about the background of the problems. And also, we need to install the basic and necessary libraries to make the preparation. Here is a list of libraries. Okay, let's move on to data. We can find the data from this website, this link. And on the website, we can download the code to import data. So we move on to EDA. We need to see the description of the data information. So the first one, we can see the shape of the data set. And then we need to check whether there is some missing values. Also, we need to check whether there is some duplicate numbers, and also to make sure that how many numbers of unique values in each feature. And also we need to know the information. And then we want to know the skewness of quants and encoding the post type. And then we need to check skewness of target. Also, we try to use Tukey rule outliers for target. And then we can draw a box plot Y to check outliers. Okay, let's go to see the results. Here is the result of the code downloaded from the website. And we can see that this is the dataset. The shape is 4,177 rows times 8 columns. And this is the basic statistical information: the length, diameter, height, hole weight, shaft weight, and a lot of things like this. This for range, shell rate, rings. And we can see the data type, expanders, and data columns. Also, missing value here is 0. Duplicate value check is 0 too. And this is the pictures. The first one is the distribution. It is right skewed. And here is the ring count box plot. The target variable skewness is 1.114. And the target variable is rings with age, calculated as age is rings plus 1.5. So the rings range is from 1 to 29 rings, converting to 2 to 30.5 years. So let's go into the result of feature code encoding. The implementation is successfully encoded MFIS012. Here you will see M is 2, F is 0, I is 1. And we use the Tukey rule outliers for target price pins. So here is the result. So the outliers detected, but flagged not removed to preserve data integrity. So we need to consider that outliers may contain valuable biological information. Okay. So let's go to the most important part. This is a critical validation step, is how to split data and make standardization. First, we need to split the data. We made the test size is 0.2, it means 80 to 20 training versus test set split. And the random state is certain is 0. Okay. Then, why we use standardization? It is to prevent data leakage, because test set cannot see training statistics. We run the random forest regressor of feature importance. And we use the visualization to show the results. It's more vividly. Okay, let's see. Here is a random forest feature importance analysis. You'll see shell weight is the strongest predictor. It shows biological relevance. Sex has minimal impact, so it makes similar growth patterns across genders. So the practical implication, we should prioritize the first 3 to 4 measuring of features. The rest one is not so good. Okay. So let's go to the models we use to make the comparison to show their performance. We use 8 models, and it covers linear models, regularized models, tree models, ensemble models, and neutral networks. It's a complete complexity spectrum. So let's going to see the results. We need to see the report performance. Okay, like actuals, predictions, like the results. Okay, here the first one is multiple linear regression. It shows an MSE, MAE, R square, and the maximum absolute error. If the R square is bigger, it shows the variance is bigger. It also shows that it may be over it may be okay. Higher variance shows prone to overfitting, but it also shows low bias in sometimes. So let's see in conclusion what their performance shows that. So if we have a higher R square, it means the better performance. So MLP neutral network is the best. And it's also low bias model, but it may prone to overfitting. And the worst one is decision tree. It's only like here 0.37. It's not so good. Here is the results. So the high bias models like low R, it's like linear family with low R squared, and it may have underfitting risk. So regularization effect is limited improvement with loss of ridge, but the medium complexity models is like the ridge multiple k nearest. So okay, so the Russell is not the worst one. It's in the middle. Lasso is bad, but Rage is in the middle. Sorry, I made a mistake. Okay, so we need to see the report performance. Let's use the best example to see the performance. Here is the actual versus predicted. It's a positive relationship. The red line is perfect prediction line. Here is the residuals versus predicted values. This is a distribution of residuals, and there is the error cumulative distribution function. So here is the information of the statistics, error statistics. Okay, so let's go to the summary. The multimetric evaluation, MSE, means emphasizes large errors. MAE means intuitive interpretation. It means average ring error. And R squared is explained variance proportion. Maximum error is worst case scenario analysis. Okay, let's do the summary. So the best model is MLP neutral network. The mean absolute error is 1.49 rings. It's about this year's. proportion of variance explained is 58.8%. It's not very high, but compared to other ones, it's so high. It's very high. Okay. So here is a comparison with the traditional method. Its cost high if you use traditional method, but use machine learning method due to a cost low and with fewer with less time and low but a little bit more error. So the Bayes variance trade-off demonstrates its full model complexity spectrum, random forest no, the MLP from the best. But it also showed high variance risk. It means the MLP, yes. The validation methods is proper train test splitting, data leakage prevention in standardization, multi-metric comprehensive evaluation. In the model comparison, we use 8 models. So the business impact analysis is there is 1.49 error. It is acceptable for mature app learning. The efficient gain is minutes versus hours per sample. Cost reduction, automation lowers per unit cost. Measurement simplification. The priority measurement is shell weight. Consider omitting sex measurement. It's only like 0.5% important, so we can omit it. The sustainable agriculture, accurate age to appropriate harvest timing. The second one is avoid premature harvesting to populations to make populations sustainability. Here is some improvement recommendations. The first one is feature engineering. You need to create ratio features like shell weight to weight. And second one is cross-validation. Use K-fold for more robust estimate. Then is hyperparameter tuning. Grid search for optimal parameters. Then ensemble methods. Try gradient boosting stacking. So here is the final summary is this project demonstrates complete ML workflow from data pre-processing to model evaluation, with special emphasis on Bayes variance trade-off and validation methods, providing a feasible automated age prediction solution for the app learning industry. Thank you for watching.